This section focuses on Chapter 3, Acids and Bases. It's a review. You want to see Table 1 for the pKa's, which are on page 98. You should memorize these values because it's going to help you keep in mind relative values of acids and bases. While we do want to minimize memorization in this course, it's good to have these values in mind. I've listed them here under various acids and bases, and you can rationalize these pretty easily based on their pKa's and chemical structures. For example, sulfuric acid is a strong acid, and if you consider the subject of this acid in particular, let's cross out that 3 on the SO3 and draw in the chemical structure of sulfonic acid, or sulfonic acid. And what you can see here is that the structure is very similar to sulfuric acid, which makes sense that it has a pKa of -1. When you go to the next compound on the list, this protonated version of acetone is going to be very acidic. You can keep in mind that these R groups, while they're drawn as methyl, can be anything. And this is going to have a very low pKa, meaning that it's highly acidic. You already know that hydrochloric acid is strongly acidic, and you know that the hydronium ion is very acidic. You probably remember that acetic acid is one of the more acidic neutral compounds, and that's because of the delocalization of the negative charge over the carbonyl and oxygen. Let's just go ahead and draw it. You get a resonance stabilized. Let's draw the resonance hybrid. You get a resonance stabilized anion. And because of that resonance stabilization, that's why that pKa is so low. Similarly, with malonic anhydride, you have a negative charge in that conjugate base that's delocalized over 2 different oxygens in those carbon atoms. Likewise, in phenol, you have a negative charge that's delocalized over an entire benzene ring. Water, we know, is not very acidic with a pH of 15.7, and likewise, alcohols are very similar in pKa. Acetone itself, I meant to label with a green hydrogen, has a pKa of 19.2, so this is at the level where you can handle acetone, and while it will absorb into your skin, it's used in nail polish remover, for example. It's not acidic, so it's not going to harm you in the same way that acids will, although it's not unharmful. Acetylene is the gas that's used in torches for welding. Also not a very acidic compound, but it's worth noting that the pKa of 25 is lower than the pKa of sp2 and sp3 hybridized carbons, and that is due to the hybridization of those carbon atoms. It's important to be able to predict equilibria to when you're considering acids and bases. And we want to predict the side that has the lower pKa. We know from that chart above that we're going to favor the side of the products here, but we don't want to know that because we've memorized that table. We want to know it because we understand that the phenoxide has an sp2 hybridized oxygen atom, and when it is deprotonated, the electrons that are in that oxygen atom are not on the oxygen atom itself, but are delocalized in the benzene ring. You can write them on 3 different carbon atoms. I'm just drawing them for one of those cases. But you've got 3 good resonance structures for phenoxide. So I'll give you a minute to practice drawing the other 2. Notice that I'm using resonance arrows, not equilibrium arrows. Let's consider another equilibrium. Here we've got acetone, which we will learn later is subject to nucleophilic attack at this carbonyl carbon and can undergo reactions that result in the formation of this intermediate, but we're not going to worry about them now. The reason that I bring this up is that we need a non-nucleophilic base in order to carry out deprotonation at this alpha position instead of nucleophilic attack. So our acid-base reaction is going to be one where we remove this alpha proton. Does this favor the right or the left? Well, LDA, or lithium diisopropyl amide, abbreviated as LDA, we don't know the exact pKa of this from our pKa table, but we know that it's going to be around a pKa of 38 because of that value for ammonia being at 38. We also know that the pKa of our carbonyl is going to be 20. So when we consider the equilibrium between these two sides, we want to favor the side of the higher pKa value. Thus, we favor the right side of the reaction. Qualitatively, we can think about acids and bases as the strength of the conjugate base, or B minus, and the more stable that conjugate base is, the more acidic the acid is. There are some rules, there are 5 rules for considering the strength of conjugate bases, there are 5 rules considering the strength of acids. Your book only talks about 4, but I'll talk about all 5 of them. The first is the atom that's bearing the charge. The more electronegative an X or an HA unit is, the more stable the conjugate base is. So, for example, we know that hydrofluoric acid is more acidic than water, right? And we can follow that through the entire first row and the second row. What's also important is that the larger size of the atom, so we'll actually follow the opposite of electronegativity here. The larger size is the more stable. So while fluorine is more electronegative than chlorine, we have hydrochloric acid is more acidic than hydrofluoric acid, and the same for hydrobromic acid and hydroiodic acid. And that can be rationalized based on the negative charge being more delocalized over a larger space over that larger atom. Resonance means that compounds are more delocalized. The more delocalized they are, the more stable they are. One classic example of that is comparing ethanol to acetic acid. Again, we're looking at the equilibrium with the conjugate base. In the example of ethanol, there are no resonance structures. In the example of acetic acid, we have 2 resonance structures, giving us this resonance hybrid that we drew already. And because we have this resonance structure, then that's more delocalized. Another way we can explain this is that this oxygen atom and this one as well are sp2 hybridized, which means that the orbital that houses the negative charge is closer to the nucleus, and therefore that proximity to the positively charged nucleus allows for greater stabilization. So you can think about this as resonance stabilization or sp2 hybridization. Either way works to explain this concept. The typical example that's given for induction is a comparison of acetic acid versus trifluoroacetic acid. Here we've got, if we consider, I'll just draw the conjugate base of trifluoroacetic acid. So in trifluoroacetic acid, not only do we have the delocalization throughout this pi system, but we also have the inductive effect of these fluorine atoms, which are our most electron withdrawing atom that wants negative charge. So by giving it negative charge, then we have destabilized the conjugate base. So trifluoroacetic acid is more of or stronger acid than acetic acid. With orbitals, here we're considering size. So let's think about SP versus sp2 versus sp3 hybridization. We should draw that. as bent. And think about the size of the orbitals in this case. In the case of sp3, we have a carbon atom that has an sp orbital that's bound to hydrogen, and we also have a p orbital and another p orbital that are used to create those triple bonds. This sp orbital has more percent of p orbital character, and that means that this orbital is shorter. It's closer to the nucleus, therefore it's going to stabilize the negative charge more than the sp2 orbital, and note that in the first example I've left out the sp orbital that would be attached to something else such as carbon, so let's include that for thoroughness. In the last example, we've got 3 orbitals bound to something such as carbon and an sp3 orbital bound to hydrogen. And these are the longest orbitals, which means that the negative charge is least stabilized. It's least stabilized when the atom is deprotonated. So we have the sp hybridized system is more acidic than the sp2, which is more acidic than the sp3. What your book does not cover is charge, which is a pretty simple concept that should have been covered in your book. And we can look at a simple example such as the hydronium ion versus water versus hydroxide. And it is important to realize that the more protons you have, the more acidic something is. That is because acids are proton donors. So it should not be a surprise that hydronium H3O plus is more acidic than water, which is more acidic than hydroxide, where the hydronium ion is a strong acid and hydroxide is a strong base. If this is confusing to you at all, you need to go back and read the entirety of chapter 2, all of it. It's not really possible to get through organic chemistry without understanding this concept. Keep in mind also PKBs. you want to think about which lone pair, or whether it's a lone pair of electrons or a pi bond, for example, in an aromatic ring or a conjugated system. You want to think about which of them is the most delocalized and can therefore serve as a nucleophile in an acid-base reaction, or as a Lewis acid in an acid-base reaction. So when we're thinking about lone pairs, we're thinking about sp3 versus sp2 versus sp, and whether they're resonance stabilized or not. If you take a simple molecule, like this one, and you want to consider whether it's going to be deprotonated at the sp2 carbon versus the sp3 carbon. Oops, I didn't mean to. There, here we go. We know that, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. My computer is not cooperating. There we go. Negative charge on that terminal carbon. I'm just going to draw this from scratch. Let's see. 2C. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Here we've got an sp hybridized orbital and an sp2 hybridized orbital. And then keep in mind that all of these in the middle are sp3 hybridized. So what we have is that this carbon is more acidic than that one, and everything in the middle is even less acidic. Although you should keep in mind that there are resonance stabilized hydrogens here, so they're going to have more acidity than this blue carbon in the middle. But it won't really matter because you're going to be deprotonating the acetylide carbon before you deprotonate any of the others. That is all for this lecture.